Hi, I'm going to have a look at how to work with elliptic curve cryptography and cryptocurrency transactions at a low level in microcontrollers. The async cryptography that Bitcoin uses is elliptic curve cryptography. So here is a brilliant blog post which introduces you to the concept of elliptic curve cryptography. And here we have the basic formula and some examples of elliptic curves. You can define a group of points over an elliptic curve, and these have useful properties for cryptography. The relationship of these points on the elliptic curve give rise to a useful property referred to as a trapdoor. So a trapdoor is basically something that's easy in one way and difficult in the other. Working with these points on the elliptic curve is more of the domain of cryptographers and mathematicians. Thankfully, there's libraries that exist. This repo here, micro-ECC, lets us do elliptic curve cryptography in a 32-bit microcontroller. So if we look at the examples, we can see what we can do with this micro-ECC library. With a specified elliptic curve, we can make public and private keys, and we can sign data. Now, we've seen that we can make a public and private key using this micro-ECC elliptic curve cryptography library in a microcontroller, but the public and private key that is generated with this library is not the same as a public and private key of a cryptocurrency project, as a cryptocurrency project will have a specification for what makes their public and private key. So let's have a look at how to make a Bitcoin public key, for example. So here is the documentation that outlines how to make a Bitcoin public key. So we take our public key generated by the elliptic curve cryptography. We perform a SHA256 on the public key. We perform a RIPEMD-160 hashing on the result. We add the version byte. We then perform a SHA256 hash on the result. Then we perform another SHA256 on the result. We take the first 4 bytes as a sort of checksum, and then finally convert the result to base 58. In order to do this, we will need a few other libraries. The first results that I came across for these libraries was a locked repo for Trezor Crypto, Trezor itself being a hardware wallet. We have SHA256 and we have the RIPEMD-160. In my main file, I define the elliptic curve, create the public and private key using the micro-ECC library, and then we go about creating the Bitcoin public key as per the specification. We do a SHA256, then we do the RIPEMD-160, add the version by double SHA, append the checksum base 58 in code. Here we've created a public Bitcoin address. Okay, so I'm going to now have a look at what's actually involved in signing a cryptocurrency transaction. This is the Bitcoin white paper, and here's a high-level diagram of transactions. Now I'm going to start drilling into the details of what actually has to be done to perform a transaction. So as we can see here, unspent transactions have to be provided as an input to create the raw transactions, which is a potential issue when dealing with the limited resources that a microcontroller has. As a signer needs access to the unspent transaction inputs, some sort of mechanism to serialize them is needed. And that brings us to Bitcoin Improvement Proposal 174. BIP 174 defines the serialization and deserialization mechanism for all of the data needed to sign a Bitcoin transaction. So here's the specification. We have detailed all of the keys for the serialization specification. So you can use Bitcoin Core and most other wallets to create a pre-signed Bitcoin transaction that you can then sign with a hardware wallet. To look at the actual practicalities of working with a pre-signed Bitcoin transaction in a microcontroller, I'm going to be using this library, libpsbt, because it lets you step through the PSBT. I've got a CMake project that uses this library, and I took the test routine from the repo and just added more printf functions so I could see the attributes of the PSBT. Using the PSBT read from the library and passing a callback, which is called for each element in the PSBT. So if I run this script with an example, we can see all of the attributes in it. We have input transactions, then we have output transactions, and then we have various records related to the transaction to be made. So there is some pseudocode which shows us how to handle the PSBT. How we actually do signing depends on what data is present in the PSBT. So for each input, you're going to have to then pass the serialized data again to see if other data is present so that you can determine what type of signing needs to be done. Once you've identified the SIG hash to use, you build up the data that is to be signed, and then you sign that data. So this is definitely a non-trivial problem to do in a microcontroller. And it kind of feels a bit messy. Anyway, good news is there are some libraries that have fully implemented the specifications of cryptocurrencies and that can run inside microcontrollers, specifically 32-bit microcontrollers. Here is one such project, MicroBitcoin. Another project is libwally core. Using an ESP32 and the Arduino IDE, let's have a look at the MicroBitcoin library. If we go to libraries, it does actually exist in the repo, MicroBitcoin. And here we've got a pre-signed Bitcoin transaction example. So we're passing a base 64 encoded pre-signed Bitcoin transaction. It's printing out the transactions, and then it does a sign. We've got the outputs of 150 and then a printout of the now signed pre-signed Bitcoin transaction. I did originally think that a signer merely signed some data, but with Bitcoin at least, a hardware signer has to do a bunch of logic related to the version of the transaction. In conclusion, signing a cryptocurrency transaction in a microcontroller is a non-trivial problem, but there exist mature libraries that you can utilize to make a bespoke hardware signer.